Hello, these are generated images from a new model, actually a new class of model. It's been around for a while, but for the first time, this new class of model has been pushed to the point where the images they produce not only look really nice and look like something you've come to expect from the latest and greatest GAN models, but also they are better in the standard metrics we use to evaluate GANs, specifically here in the FID, the Freshe Inception Distance. So the paper we're going to talk about today is called Diffusion Models Beat GANs on Image Synthesis. It's by Prafulla Dhariwal and Alex Nicol of OpenAI. Already in the title, they're pulling no punches. Just be like, this beats GANs. Okay. So in this paper, they're mainly talking about improvements to this new class of models, which they call diffusion models. Now, I would like to dive a bit more into what diffusion models are instead of just telling you what the improvements of this paper are, because I think most people haven't come in contact with these types of models yet. So they thoroughly reference another paper which is called Improved Denoising Diffusion Probabilistic Models by themselves. And in this paper, they more develop these new models than in the other paper. The paper here, as you can see, it's just like 3 months younger than the other paper. So this is really close. I think this paper is more insightful into what these models are. That being said, by the name improved right here, you can also see that this is not kind of the seminal paper of these types of models. So if you're interested in that, you have to go back even further. However, we're going to look at this and we're going to look at the new paper and see what are all the things that lead to this new class of models being better than GANs. Specifically, we're going to talk about DDPMs, denoising diffusion probabilistic models, and they're a bit like a variational autoencoder, like a little bit. Yeah, but we'll go through that. All right, so if you feel that this was helpful, please do share it out. It's been a pleasure bringing this to a lot of people, and if you do, it will just be more people. We'll have more fun. Right, so they say that denoising diffusion probabilistic models, DDPMs, are a class of generative models which have recently been shown to produce excellent samples. Okay, and we show that with a few simple modifications, DDPMs can also achieve competitive log likelihoods while maintaining high sample quality. So in this paper, they take these models, these DDPM models, and they say, look, we can push those models to push their log likelihood. So there are a number of metrics that generative models track. It's not as easy as kind of the validation set accuracy in a classifier. Log likelihood is one of the metrics that these models track. And here they say, well, we can get competitive log likelihood while maintaining high sample quality, which is a nice way of saying we don't beat GANs yet, right? In the next paper then, the one I showed you before, they actually do beat GANs on the standard metrics, and also the samples look quite impressive. So DDPMs have been around before, but they go into a quick overview right here, which is what I think is quite appropriate for us to dive in. So the philosophy here, or the whole purpose behind this is, they say, let's imagine I have an image, right? I have an image of, I don't know, my house right here. I have an image of a house. And I define a process, what they call a forward noising process. And this forward noising process takes the image and it just adds a little bit of noise to it, like epsilon noise that's sampled from some standard distribution, like a Gaussian, okay? So you just sample a bit of noise, and you just add it to that image. So you have the same house, but there'll be a bit of noise on it, okay? And then you do it again, okay? So you sample another bit of noise, and sorry, this comes from this distribution, and you do it again. And as you do this over many steps, and here they notice that the previous authors were using 1,000 steps, and if they just increase that to 4,000 steps, like the log likelihoods go better. In any case, you do this for many steps, thousands of steps in this first instance. You do this, what are you going to end up with? Well, the argument here is that if you do this for so many times, for so long, over so many steps, you're going to end up with random noise itself, right? So this is ish, according to some kind of normal distribution, okay? You just assume, right? And you can actually prove this, that if you do enough steps, like if you do infinitely many steps, and it goes actually towards just noise. So whenever you're done with this, there is like no more information about the original image than actually sampling from this distribution right here. So you've successfully defined a process that takes you from the image space, right? This here is from the data space. That takes you from the data space to a known distribution, which is the normal distribution. Now, here is the kind of the logic. If we could invert this, like if we just somehow could invert this mapping, right? If we could have a process that knows, if I give you an image with some noise, can you tell me what image that came from, right? Is that doable, right? And it's thinkable, right? If I give you like this image with some specks of noise on it, and I ask you, could you please give me, like, I tell you, I'm the oracle, I tell you, look, I've taken some image, right, that already had a bit of noise on it, but I've added more. Like, I've taken an image, I've added some noise. What was the original image that I don't tell you what the noise is, right? I just tell you the noise comes from whatever, a normal distribution, I've added it. What was the original image? Now, you looking at this image, you'll see, this could be a house. So not quite sure, but, this might be something like this might be the original image. And this here, I'm not really sure about if this is noise. So you're going to sort of revert that process a little bit, right? Knowing that this is how the image came to be. You, as a human, if I told you, you could approximately reverse that process. That, of course, requires you to know something about these images, right? It requires you to know what a house looks like. And when you see something like this, that, well, probably, because I don't tell you which ones are the noise and which ones aren't. So that's the trick, right? If I just told you, well, all the orange stuff is noise, right? But you just see this all in monocolor. But kind of, okay, so this here looks like it's from the image itself, but then this here is just kind of a speck, and that just kind of might just be noise, maybe not, right? But then this here, I'm pretty sure it's just noise and not part of the original image. So you could do that. And the question is, can we learn a function that does this reverse process? If we can do so, right? If we can learn a function, of course, that's going to be some kind of neural network-ish thing. If we can learn a function where I give you an image with noise, and I tell you, by the way, so this is maybe time step 0. Here, this is t equals 0, t equals 1, t equals 2, and so on. Well, you can't see that. If I tell you, okay, here is an image. This happened at t equals 50. Can you give me the t equals 49 image that this came from? All right. And this is the whole principle. We're going to, we can generate training data for this neural network very easily, because we just take data and we run them through the noise process forward, right? Then we have plenty of training data for every step of this pipeline, right? In fact, we don't train a different phi function for every step. As you can see, the phi function simply takes the time or can take the time as an input. It's certainly possible otherwise, or it's possible to not tell it at all, right? Then it has no clue. So yeah, if you do this, you can generate training data, and then the idea is you can just run this process in reverse and arrive at the original sample. And even more, because this here is actually the normal distribution, you can now sample random noise from that normal distribution, right? You can feed it to this process, and this process, who has learned to map the data distribution to the normal distribution and can reverse that process, will give you some sort of data distribution sample for your input that you sampled from the normal distribution. All right, this is the idea, and it's quite tricky to get this to work, as you can imagine, but let's not forget that GANs also have been quite tricky to get to work. It's just maybe there has been a bit more work going into GANs. All right, so formally, this goes as follows. We define this forward noising process, right, we sample this from the data distribution. We sample x0 from the data distribution. We define this forward noising process Q, okay, which produces x1 through xt. So capital T is the end here. And we, by adding Gaussian noise at time t with some variance, okay, so you can have it's zero mean Gaussian noise, I believe, maybe. Yeah, it's, well, you scale, but you define this variance schedule right here. That's also your choice, right? You choose what kind of noise you want to add. But ultimately, you take the distribution of the things you produce via that noising process, given that you start at the data sample x0, you simply define as this product of distributions. So you start with, this just means you start with x0, and then you go from x0 to x1, and then you go from x1 to x2, and so on, okay? And each of these steps is an independent application of noise. As you can see here, this is one of those steps. So what you're saying is that the distribution of the next sample right here is going to be a normal distribution that's going to be centered at this thing right here, and its variance is this thing right here. So you can see that the assumption here is you use noise that has a diagonal covariance matrix, okay? This is, I guess it's reasonable. It certainly makes computing things easier, right? The other thing here is that you can see this Gaussian is centered at the last sample, but downscaled by this factor right here. And I think, like, this is a choice again by the modelers, but I think this is also due to the fact that makes computation easier, because I guess if you don't have this, then you know, you start somewhere and you add noise and you sample something, you add noise, you sample something. Maybe this would grow indefinitely, and you sort of need to rescale things such that you can make this statement right here. Given sufficiently large t and a well-behaved schedule of beta, the latent xt, so the very last step, is nearly an isotropic Gaussian distribution. Okay, that's the entire point. So if you do it like this, which is a choice, but if you do it like this, then at the end, if you do enough steps, infinitely many steps, then you end up at an isotropic Gaussian distribution. Thus, if we know the exact reverse distribution, we can sample from the Gaussian and run the process in reverse to get a sample from the data distribution. Then they say, however, since the reverse distribution depends on the entire data distribution, we approximate it using a neural network as follows. So this statement can be a bit weird in first instance. This depends on the entire data distribution, right? Because it's very close to this thing right here. And this thing right here depends on nothing, right? This you just define. You just say, I'm going to add random noise to something, and that's my next distribution. It only depends on the input image right here. The way to see it, that the reverse depends on the entire data distribution, is exactly what I said before. If I give you if I give you this picture, I'm not going to actually tell you, right, where the noise is. So I give you this picture, and I tell you this is a drawing from a very small child, because that's my drawing level, and I've just added a bunch of noise to it. Could you tell me what the original drawing was, right? This is very different from me saying, here is a drawing from a small child, please add noise to it. That's easy. I just did this, right? I was just, oh God, I just did it. But if I tell you what was the original image, you have to take into account the entire, world. Like, about how small children draw, what kind of motives they usually draw, and so on. And that's how you are able to come up by saying, well, it was probably something like this. So this needs your knowledge of the entire data distribution. That's why they say it right here. Okay, so they say, well, we can't just have the entire data distribution, otherwise, we wouldn't even have the problem in the first place. So what we can do is we can approximate one of these steps using a neural network. Okay, so we have a neural network that takes as an input, as I said, it takes as an input the noised version of the image, and it gives you as an output, it's a bit like this is, it gives you, I told you, give me the image that this came from. In this case, what they want is, give me a distribution over images where that could have come from, right? And again, they say this, they model this as a Gaussian right here, and the neural network will produce the mean and the covariance matrix given the image. So the neural network is supposed to look at the image and decide, okay, what's the Gaussian distribution of images where that probably came from? And this is a strong assumption, right? The fact, for example, that this is a Gaussian distribution, like this is adequately modeled as a Gaussian distribution. It's a strong assumption that you can only make because you make these very small steps. Because nothing stops you from actually doing this in one step, right? Nothing stops you from or taking, the data distribution, just adding like a wild bunch of noise, because then you're also approximately normally distributed. Maybe not, I don't know. You maybe end up at some other distribution. But certainly, if you can do the reverse also. You can train a neural network to do it in one step. In fact, that's a little bit what GANs do, right? But if you want to do this in this sort of manner where you model all the distributions, notice this is a very different language than GANs. Here, it's all kind of in the distributional semantics. If you want to do this and you want to say, well, I model the reverse as a normal distribution, this is just not true if you took large enough steps, right? But if you take very tiny steps, you can adequately make sort of the argument that the normal distribution is kind of okay for this to work. And of course, it makes life easier after that. So they need the tiny steps, because in the tiny steps, they're able to sort of, the modeling assumptions hold. Also, I guess it works better. And then you can define the loss function right here. So they say the combination of Q and P is a variational autoencoder, and we can write the variational lower bound as follows. So I'm not sure if I've ever gone over variational autoencoders, but it's very similar to here. What you can do is you can define this variational lower bound, which essentially boils down to saying, I would like the distribution that I want to model and the thing I actually output to be close together, right? So this is the reverse process that my neural network does. And this is the thing that I actually would like to model, okay? And this is the thing that needs the entire data distribution. We're going to look at that in just a second. So yeah, there are some other terms here, but you can get around that. And the last term right here, like the last term, you just assume that's kind of a Gaussian. So really it comes down to, does the distribution that your neural network outputs match what it actually is? And here you can see the sort of proxy for, well, this needs the whole data distribution is the following. If I tell you that this is the process by which I derive the data, right? And I ask you, what is the reverse distribution of one of these steps? You can't possibly compute that, right, accurately, because you don't know the data distribution. However, what you can do is, for this particular sample, you can compute it if I tell you that, this is the process by which I derived it, and also if I actually give you x0 right here. If I give you that, then you can calculate, and that's what they show here. You can actually calculate this distribution. You can say, what is the actual distribution I'd like to model? And that's going to be a normal distribution. But it makes sense, right? In this case, like if this is the forward process, and I give you x0, if you already know the result, you can calculate the distribution. So that's what they derive right here. And that is dependent, of course, on your noise scale, which is like all over the place in these formulas. But you can calculate that, and this is a Gaussian, and they model the output of the neural network as a Gaussian. So these KL divergences they become really easy to calculate. And then you have a loss function. So now they say, how do we actually train this thing in practice? Because it turned out in the last papers that this thing right here, the actual variational lower bound, isn't too effective. I think that's what they're saying. So yeah, what the authors here say is they go back to a previous paper. They say the previous paper found that modeling the noise here is the best way to do it. So the question is, what exactly does the neural network do? Like, the neural network could do many things. It could actually just predict this mean parameter, which we've talked about, right? The neural network could simply, I give you an image and you tell me what's the most probable image where it comes from, or sort of the mean, and also give me the covariance. But also what you could do is you could just model the noise. That's a different thing. You could model the noise. And that's equivalent from a computational perspective, right? Or from a conceptual perspective. If I give you, again, this image, you can either tell me where it came from, or equivalently, you can tell me what's the noise that I've added, right? And you tell me you've probably added this noise. Right? both the same from an information perspective. However, the authors previously noted that the modeling the noise is better just from a neural network training standpoint. In fact, they make a point here to define a new loss function that simply says, well, the noise that I output from the neural network should approximately match the actual noise that I've added, right? Because I know what noise I sampled in my forward noising process. And that works better. However, these authors here say, okay, this does not tell you anything about the covariance, because that only tells you something about the mean. And the old authors found that we don't actually need the covariance. We fix it, and that works a lot better, or equally well, to actually learning it. And the authors here say maybe they've missed something. Maybe they've missed the opportunity to learn the covariance. So this was a little bit of a rant, but to repeat, we define this noising process, and then we try to learn a neural network that reverts that noising process. In order to do so, we train a neural network to reverse each of the little steps that we do right here. And the way we do it is the neural network will predict the distribution of the predecessor. So given a noised image, the neural network will output the distribution modeled as a normal distribution over where that noisy image probably came from. And the previous authors have said, well, there are two things to model. There is the mean and the covariance. And we find, first of all, if we just fix the covariance, that's enough, right? We fix the covariance matrix to the noise scale that we know we applied, and good enough. We don't actually need to model the true covariance matrix, just from an empirical standpoint. And then when we model the mean, we don't model the mean directly. We actually model the noise, and which is equivalent, but it works better from a neural network standpoint. The authors now say, maybe you've missed an opportunity learning that covariance matrix, because it's one thing to say this is probably a Gaussian, right? It's another thing to say this is probably a Gaussian with completely isotropic covariance matrix. You would expect the second one is easier, but also it's more wrong. So that's what we go about here. So they say, can we improve the log likelihood right here? And the first topic they go into is learning this covariance matrix. And what they discover, I want to say, is that if you fix the covariance matrix right here, you have to know what scale to fix it at, which is dependent on the noise that you applied in the forward process, right? So you applied some noise, and you can calculate what the average covariance of the reverse step should be at that particular time step. And in fact, you can derive an upper and a lower bound. So if beta here is their schedule for noise, then these are the two bounds. So this is the actual beta you used in that step, the noise scale, and this is sort of an accumulated noise scale up until that step. These are the two bounds in which the noise can be, right? The noise level or the covariance. And the previous author said, well, we can use either one of them. It's actually fine. It doesn't matter. And these authors say, okay, look at this right here. This is the ratio between the two. So the ratio between the upper and the lower bound as a function of the diffusion step. Now, especially if you go to a large amount of step size, you see this immediately clamps at 1, right? So there is like almost no difference between the upper and the lower bound, which is probably why the other authors estimated it didn't matter. Now, these authors go further and they say, well, if you just try to learn like a number, neural networks are kind of bad at regression, right? So if you tell a neural network, learn me any number on the number string, whatever you call that in English, if learn me any number, like here's 1, here's 2, here's 3, like here's 500, any number whatsoever. But, however, the only actual right answers are going to be a tiny, tiny sliver between like the ratio between them is going to be a tiny, tiny sliver somewhere in like 3 orders of magnitude down. The neural network's going to have trouble hitting these correctly. So the way they do it is they reparameterize the how they predict the covariance matrix. In fact, what they come up with is they simply learn an interpolation parameter, v, right here, to interpolate between the upper and the lower bound. And that turns out to be quite a good decision, because now the neural network can predict a number, v, for each dimension, which is between 0 and 1, right? And that's, neural networks can predict stuff between 0 and 1. They're pretty good at it. And the whole rest, the whole scale issue, will be taken care of by interpolating between the two valid bounds. So this is one thing. They're able to learn the covariance matrix now, and that boosts them a bit. And then they also look at the denoising process right here, and they say, well, if you look at this, and this is something I find a bit shady, but they say, if you look at this, and this top row is what is currently done with the noise schedule that is usually defined, it's just kind of noisy a bit too much, right? Like from here on out, there's just noise, right? Could we not schedule this a little bit such that the drop-off is more gradual? That might help a lot. And so they come up with a new schedule that does this. Now, this seems very subjective, right? You know, this is you as a human looking at it. They do some experiments here where they say, we measure the inception distance as we just leave away a fraction of the reverse diffusion process. So they wonder, how many of these steps can we just leave away and still end up with something that's fine? Like, can we just skip the first step of the reverse process and start here? Can we skip 5 steps and start here? It turns out in the linear schedule, you're just able to skip a lot more steps, which gives you an indication that those steps weren't really helpful, and it'd probably be better that you define a schedule where all of the steps are helpful. So that's what they come up with. You can see the linear schedule right here is dumping pretty fast, like it goes down pretty fast, while their new cosine schedule is much, much slower. Like these are now actual practical considerations that are just done by kind of looking, evaluating a bit empirically, and then going and saying, well, can't we do something better? Now, this something better, they admit that themselves, isn't by no means the best thing you can do. It's just something better. Like, ultimately, you would want the same step in the denoising process probably to contribute equally to the quality of the entire system. You know, but that's what they do. The last thing is very similar. They say we reduce the gradient noise. So they observe, if they use... they have now 2 loss functions, right? They have the original loss function, where you simply look at the L2 distance between the noise and the predicted noise. Like no variational lower bound, yada, KL divergence. Who needs that? Crap, right? That's what they call the simple objective. Now, the simple objective doesn't contain the covariance. So what they would like to do is they would like to go back to the variational objective. And that's the blue line here. I know you can't really read it, but... that's the blue line here. And you can see, not only is it pretty noisy, it's also, well, okay, I guess it's pretty noisy, the loss curve. If they mix the variational objective together with the simple objective, they get a better loss curve. You see that right here. This is this hybrid loss. It's the orange loss. It's still noisy. Their new loss, which they call resampled loss, That's again the variational lower bound loss, but sampled in a different way, is the green line, which is much, much smoother and also lower. And that comes from this fact right here. If you look at not from this right here. Where is it? Okay, so what they say is, if you look at the process, like this noise process here, and you look at where the actual loss comes from, where does the majority of the loss contribution come from, they notice that the majority of the loss contribution comes from the first steps. So there is a real imbalance of how much these individual steps in the noising process differ from, like, contribute to the overall loss. And they say, well, if we just add all of them up equally, right? Because what do you need to do to train these neural networks? You need to start off with a clean image, then sample some step, like some step. You say, okay, I'm going to now train the t equals 205 network, right? So you add noise 205 times. You can do this in one go, by the way, but essentially you add noise 205 times. You get here, right? You add noise once more to here, and now you have your training sample right here. You can calculate the distribution you want to match by also including this one, as we discussed, and you're good, right? So this is one training sample. The next training sample is you select a different t and you produce another training sample, and so on. Now, if the first few steps are much more important than, the step at t equals 5,000, and you're just sampling t uniform, you will end up with, a correct, probably unbiased estimate of your loss. However, it will be super duper noisy. So they're saying, can't we just focus a bit on where the loss actually occurs? So they devise a scheme to do importance sampling. Okay. Notice that the different terms of the variational lower bound have greatly different magnitudes. In figure 2, which one's figure? Oh, figure 2. Ah, there we go. That was the plot. So here is the step in the noising process, and here is the loss term magnitude. And you can see that the first few steps, they have a really like a larger loss. This is a log scale right on the left than the last ones. So they devise an importance sampling scheme to counter that. This is not specific, right, to this particular technique. You can use this anywhere where different samples have very different contributions to loss. You can choose to focus on the ones where the loss is high, and that will give you a biased estimate of your loss. However, it might decrease your variance by quite a bit. And that's what they end up with. They in this paper, they end up with something that's competitive but not better than the best GANs. However, it already looks pretty good. They also investigate model size, but I don't want to go into this. I actually want to jump quickly into this next paper, where they improve again on their models to make them actually better than GANs. And the improvements right here are much more, I don't know, I want to say boring, because it's like, okay, architecture improvements. So we're going through the same process that we've gone through with GANs, where it's like, well, here's a tweak, here is an architecture, a better architecture, here's kind of a better loss function, regularizer, whatnot. And it's quite conceivable, right, that these models here come to the level of GANs. Now, whether they are actually, better than GANs, I think this remains to be seen, because, it also depends quite a bit on how much compute you put into this. And then you also have to see that here, you have to, when you want to sample a sample, you have to input the sample and then do this denoising process a bunch of times, like thousands of times, until you end up with the data sample. Now, they do have a kind of a trick going into another model class where you only have to have, they say, 25 of these steps. So it's pretty cool, but still that's 25 forward passes through this neural network that predicts the denoising, where a GAN is just like you sample once the latent, you ship it through the GAN, and you end up with a sample. And I'm actually wondering if GANs could take some sort of lesson from here. We'll look at this after we look at this right here, which is what I think is the kind of cool improvement that they do in the new paper, which is where they say classifier guidance. So they say if you use GANs for conditional image synthesis, so if you conditionally if you use a GAN to create images that are of like a particular class, conditioned on a class label, they make heavy use of class label. Okay, so they say it makes sense to explore different ways to condition diffusion models on class labels. We already incorporate class information into normalization layers, so you have different normalization layers for different classes. Here we explore a different approach, exploiting a classifier to improve a diffusion generator. Okay. They say the kind of two previous works show one way to achieve this, wherein a pre-trained diffusion model can be conditioned using the gradients of a classifier. In particular, we can train a classifier on noisy images and then use the gradients to guide the diffusion sampling process towards an arbitrary class label. In this section, we first review two ways of deriving conditional sampling processes. We then describe how we use such classifiers in practice to improve sample quality. Okay. So the idea here is that if you have class labels together with your dataset, you can train a classifier on not only the dataset, but also noisy samples of that dataset, right? And then you can use that classifier in order to guide the process, right? So this is what we're dealing with right here. They say, well, instead of simply reverting the process, which would be this part right here, like instead of simply reverting the noise process, if I tell you what label that image is from, like what class that image is from, can you do a better job, right? So if in our original example, if I give you a noisy picture of a house and I tell you, well, by the way, this is a house, you're much more able to tell me what the original image was, or alternatively what the noise is that I've added to the image. So if you write this as a distribution, as we did so far, you can say if you want to predict the previous image from the next image and the class label, and you can pull this apart into these two components, which is the old component, like how likely is the previous image given the noisy version, times the what they call this the prior, right? They call this prior. You can see that if you just like kind of ship this out, it just swaps. Well, I don't know how to explain this properly, but I mean this is just probability manipulation. So if you have a probability product between whatever we had before and how likely is that is the class label under this. So this is sort of, you want an image that makes sense given the noisy image, but you also want an image that has a high probability of being of the class that you want to produce. Okay. And of course, this is exactly a classifier on the right, which you can use. So since our model so the question is, what are these two things, and can we sort of derive an easy form how we can work with this. So the first thing we've already seen, and we model this as a normal distribution. And if we know the mean and covariance of that thing, the log is simply this form. So you should recognize this as being just the form of the normal distribution. This here is the normalization constant. If you work in log space, that is added, and it is a constant. So if you're just interested in minimizing a function, you might as well leave it away. The second part is a bit more tricky, but you can say, well, this distribution right here, I can do a Taylor expansion around the predicted mean, right? Then a first order Taylor expansion, which becomes this. So this is, it's just kind of a vector form of the Taylor expansion if you've never seen it. So this is f of x 0 right here, and this is f of x1. This is the derivative at the point x0. How do I say it? Is the derivative according to x at x0 times x minus x0 right here. It's the same thing. Okay, so what you end up with is this form right here, and if you calculate this through, what you end up with is the entire distribution. So the product of the two things in log space looks like this, and therefore the distribution that you're looking at is a distribution. You're saying here somewhere is the image that is the noisy version. You ask your two models. You ask your first model, well, what's an image, or where does this likely come from? And that model tells you, well, it's probably from here, and the covariance is like so. Like I think that's where it came from when it was noised. And the other model simply shifts that towards, it says, well, but if you shift it a bit like this, and it actually comes from here, then it's much more likely under the classifier. Right? That's what you have. You have the predicted mean right here that says where does it probably come from, given that I've had it noise. And this part right here says, so the G is the gradient of the classifier with respect to the input. This says, well, but if I shift it like this a little bit, it becomes much more likely under the class. And given that you've already told me what the class label is, right, I'm just going to choose, I'm going to choose to shift over here. So this is what the classifier buys you. The classifier will tell you, without the classifier, I think it comes from here, but now that I know it comes from this class, I can refine my belief of where it came from. And that's how you become more accurate. Like if this is really the class it came from, you're going to be more accurate, right? Given that the assumptions of the Taylor expansion hold. Now, here, as you can see, we're really kind of getting close to the land of the GANs, okay? Now, if as soon as you have something like this, where you derive the gradient of a model, right, of a classifier model with respect to its input, and you use that gradient to sort of guide your search, that is, it's very close to a GAN. It's very close to models that do score matching. Actually, I'm very bad at explaining score matching, but it is exactly sort of this. You use the gradient of the log probability in order to model a distribution. And I wonder if GANs can't sort of take a bit of a lesson from here. Like, I wonder what happens if you don't have a GAN that just goes from noise to data, but again, like here, you have like little GANs or the discriminators at intermediate steps, right, that do their discrimination. You can generate training data pretty easily. Again, by doing this reverse noising process, you can generate training data, and you just have like little discriminators that discriminate between true data that was actually noised and data that you just produced. And by you just produced, I don't know what, I'm just coming up with this right now. This is not a prepared thing, by the way. You could probably use your existing model to somehow forward propagate, and then you noise whatever that is, right? And then you have generated data and true data in all their noisy fashion, and you can do discriminator at each level. I'm not sure. Maybe it works. Maybe it won't. I'm just saying maybe there's a way to get sort of the best out of both worlds, because this here, like if this weren't a class label but kind of a label of true and fake data, this would very much look like a GAN. And maybe we don't need all of this distribution, schmistribution. I guess it's a forever war between people who do formally corrector things and people who just throw everything out that doesn't contribute to the end quality. In any case, they also go into this DDIM models, which are a different class of models, very close here, but they say to this, and we use a score-based conditioning trick adapted from these other papers, which leverages the connection between diffusion models and score matching. So there is an actual formal connection, and you can use that to kind of, actually what I said right now, get rid of the noise in the system and directly directly predict the predecessors, and that will still end up at a formally correct thing. And that allows you, I think with this trick, they don't have to sample as much, or they only use 25 reverse steps instead of 4,000, which is important, right? And the last thing they discover like a hyperparameter. Like if you scale classifier gradients like this, you have to observe that the classifier gradients are in log scale. So technically, the way multiplication behaves with a log is it becomes an exponent right here. And that simply means that this distribution, also the normalization, that distribution is going to be more or less peaky, defined depending on that hyperparameter. And they notice that you can make it sort of more peaky, and then the sample quality becomes higher, right? I think a issue that the variational autoencoders had for a long time is that they were sort of blurry and so on. And this is a little bit, I think, how that might be fixed. Though this is the classifier gradients. So you want to make the classifier gradients more peaky, which means that you get a stronger signal from them, which apparently results in better things. So here, all the results you see whenever they say ADM, that's their model. They have several variations, namely this -G here is the classifier guided version, and whenever they say 25 steps, that is the version without the noise, with the trick connection to score matching. Yep. So you can see in sort of the FID scores, they do beat BigGAN on these tasks. Yeah, maybe the GANs will one-up taking some tricks from here, or maybe it's quite possible that these models will go beyond GANs, because we've poured a lot of effort into GANs and not so much yet into these models, into the denoising models. And the samples look pretty good. So the left is GAN, and the middle here, it's a bit small, but the middle here is their model. And I have actually, I've gone through this entire ImageNet class. I've looked at every single image to try to find these images, and I can tell you that the images are not in the training or the validation data set. These are images from the actual data set. They're pretty close, but still, I always fear a little bit that, at some point a model is just going to learn to copy the data. All right, so that was it. I know this video is already too long. If you're still here, thank you. I hope you've enjoyed this, and I'll see you next time. Bye-bye.